Welcome to this video, and today we are going to talk about physics application in MCG and biotech. Our group member consists of me, Humaira Najaha, Vilna Marcus, Nur Rehana, and Eva Nashareza. Now, I'm going to talk about thermal physics and how it can be applied to biotech. The first question is, what is thermal physics? It is the study of heat, temperature, and how energy moves from one thing to another. It helps explain things like why objects get hot or cold, how materials change when heated or cooled, and how energy is stored or transferred in a physical system. It happens via conduction, convection, and also radiation. Now, how can this concept be applied to biotechnology? We can apply it through the process always used in lab, autoclaving. Autoclaving is a process used to sterilize equipment by using steam under high pressure and temperature. Instead of explaining this rather complex diagram to you, I will simplify the principle behind it. First, heat transfer happens as steam spreads throughout the chamber via convection and conduction. This increases the pressure within the autoclave and also raises the boiling point of water, allowing the temperatures to reach 121 degrees Celsius or higher, which is important for killing microorganisms. As the steam condenses on the surfaces of the item, it releases its latent heat of vaporization, delivering concentrated energy to penetrate the materials inside the beaker. This heat disrupts the molecular bonds in proteins and enzymes, leading to protein denaturation and the death of microorganisms.
What is the important factor that ensures cell growth perfectly and valuable products are produced in bioreactor? It all comes down to one crucial thing, which is density. Density is how heavy something is for based on its size, and in bioreactor, we use this property to monitor cell growth and production of important products like insulin and antibiotics. As cell growth in a bioreactor, their density increases, meaning the number of cells per unit volume rises. By measuring this increase, scientists can determine whether the cells are growing as expected or if something needs to adjust. We also use density to separate products like insulin or antibiotic from unwanted material. By knowing how dense the product is compared to the liquid, they can separate them efficiently, ensuring only the best product makes it to the final product.
Have you ever wondered how we measure how far something can rotate? This is called as angular displacement. Let's use a clock to understand this. Imagine the clock starts at 12 o'clock. This is the initial position. If the hand moves to 3 o'clock, it has rotated by 90 degrees, which means the angular displacement is 90 degrees. Same thing happens if the hand moves to 6 o'clock. The angular displacement is 180 degrees. Angular displacement describes how far an object can rotate, not distance travel. The clock hand rotates around a fixed axis, just like this animation that rotates around a pivot point. Angular displacement is an essential concept in mathematical graphics that helping us to describe and animate rotation.
The laws of thermodynamics are a set of scientific laws which define a group of physical quantities such as temperature, energy, and entropy that characterize thermodynamic systems in thermodynamics equilibrium. While thermodynamics is traditionally rooted in physics, its principles play an important role in modern computer graphics. The zeroth law of thermodynamics focuses on equilibrium. In computer graphics, this idea is applied to maintain color balance and consistency. For example, in realistic rendering, light and color gradient must align across surfaces to create a natural appearance. The first law is the law of energy conversion. In computer graphics, this principle is central to global illumination techniques such as ray tracing and path tracing. These methods simulate how light travels and interacts with surfaces, ensuring that energy from light sources is conserved through reflection, absorption, and transmission. Next is second law of thermodynamics. The second law introduced the concept of entropy, or the tendency of system to improve towards disorder. In computer graphics, this law has multiple applications such as image compression, noise reduction, and procedural textures and simulation. Last but not least, third law of thermodynamics. In computer graphics, this relates to simulation of extreme conditions such as icy or frozen surfaces. It is also applied in optimization processes where rendering algorithms aim to reach a minimum energy state, achieving efficiency by reducing computational errors and unnecessary calculations.